The Aerosol Can Experiment by Artemisa Deni. Now, a fire is started in your home, and you have no water, fire extinguisher, or fire blanket to put it out. So out of fear, you start throwing anything you can find into the fire to stop it from spreading. As you're picking up some things, though, you notice a Febreze can laying on your countertop. As you're about to throw it into the fire, you find that on the can it says something. Danger. Pressurized container. Do not expose to temperatures exceeding 50 degrees Celsius or 323.15 Kelvin. Container may explode if heated. At that moment, you stop and wonder, why is that? Why would the can explode? Now, if you forget about the fire crisis for one moment, let's actually look at the signs behind why a pressurized container of gas explodes when exposed to heat. Now, just for some background, an aerosol is a substance enclosed under pressure and is able to be released as a fine spray, typically by the means of propellant gas. So some of the examples can be your Febreze WD-40 or hairspray and other things. And if we even took a look inside of an aerosol, we can see that the working principle behind the aerosol is actually quite simple. It normally needs two things to operate: product in green and the highly compressed gas in blue, or the propellant. And you may already know this, but as the product in the can is used up, the volume available to the compressed gas increases, or the propellant increases, until you have no product left in the can and only compressed gas. There are quite a few gas laws that are related to aerosol cans. For instance, how aerosols work lie in the vicinity of Boyle's law. As Boyle's law states that with a decrease in the pressure of gas, the volume of gas increases. So when the nozzle of a can is pressed, with a sudden decrease in the pressure of gas, the volume of the pressurized gas increases. Therefore, highly compressed gases expand drastically. As a result, gas and as well as product is forced to leave through the nozzle sprayer, resulting in that fresh Hawaiian scent you smell throughout your home. Now, when we take a closer look at the gas particles inside the can, we notice that at room temperature, these gas particles are in constant and in random straight line motion, and their collisions are rapid and elastic. Now, based on the kinetic molecular theory idea that the gas particles are going to start moving faster when heated, and so they're going to start colliding with the container walls more frequently and at higher velocities, increasing the pressure exerted by the gas, and eventually the container will rupture if the collisions get strong enough to overcome the structural integrity of the canister, and an explosion will occur as the gas escapes. More specifically, Joseph Gay-Lussac's law is sometimes known as the aerosol can law, which we'll be focusing on today, which states for a given amount of gas held at a constant volume, the pressure is proportional to the absolute temperature. Or for you math people, P is proportional to T, where P is the pressure exerted by the gas, T is an absolute temperature of gas, and K is a constant. We can also see a graph linearly. And if we look at it through the lens of the ideal gas law, whereas described the relationship between the pressure and temperature of gas with a constant number of particles at a constant volume, where PV equals nRT equals P equals nR divided by V times T, and since N, V, and R are constants, the equation would be P equals KT, where K equals nR divided by V. Now, if we take a quick look at a video doing the experiment, since sadly I do not have the facilities to perform it, we can notice the effect of heating on a pressurized container. So when we throw an aerosol can into a roughly 1173.15 Kelvin fire, we notice that we're increasing the temperature from when it is normally. Now, by increasing the temperature, T implies by Gay-Lussac's law that the pressure P will increase in direct proportion. This is true because the canister is rigid and sealed, meaning that the volume is held constant, and the gas cannot escape out either. Thus, the pressure inside the can increases rapidly with the temperature until finally, boom! This is the reason why many pressurized containers have warning labels stating that the container must be kept away from fire and stored in a cool environment. Now, after watching that fantastic experiment, let's actually do a virtual simulation together and see what is really happening inside that Febreze canister if we throw it into a fire. So first, we're going to set the volume as a constant. As we know, the gas is sealed and it's in a rigid container. Now, the typical pressure of a gas in an aerosol can is roughly 13 atmospheres. Now, we're going to heat up those particles till we see the pressure of the particles hitting the lid blasted off. So as we add in the particles and start heating them up, we notice that the particles start to move at faster velocities and start colliding on the walls more frequently, thus increasing the pressure till finally the pressure on the can is too much and it explodes the lid off, causing that rupture you would see. All in all, maybe instead of grabbing that Febreze can and almost throwing it into the fire with all your other valuable items, you probably should have called 911 first. Thanks for watching. And now you know why never to expose a pressurized container of gas to heat.